Hey there, and welcome to this explainer. Okay, if I were to ask you right now to picture a manufacturing plant in your head, what comes to mind? For a lot of us, it's this mental image that's totally stuck in the past. We picture a massive, incredibly noisy, super rigid assembly line, just churning out millions of identical widgets, right? With stockpiles of inventory sitting around in dusty warehouses. Well, today we're going to completely shatter that outdated image. Modern manufacturing has gone through a profound evolution. The ultimate goal of today's smart factory isn't just mass production anymore. It's mass customization. We're talking about the ability to build a single, highly customized part with the exact same efficiency, speed, and cost-effectiveness as making a million identical ones. It is an absolutely fascinating shift, and we're going to break down exactly how the whole shebang works.
Okay, let's dive into this blueprint for today. Here's how we're going to construct this knowledge from the physical floor all the way up to the digital cloud. First, building the flexible factory. Second, lean and just in time. Third, the industrial nervous system. Fourth, the factory brain. And lastly, the economic reality. Let's get to it.
Section 1. Building the flexible factory. To really understand the smart factory, we have to start at the micro level with the physical building blocks that have totally replaced those rigid transfer lines of the past. At the absolute heart of this physical transformation is something called a flexible manufacturing cell, or FMC. Now let's demystify that jargon for a second. Instead of an assembly line that literally only does one thing forever, an FMC is a highly adaptable workstation. It's a small unit. It might just be a single computer-controlled machine, or maybe a small group of them, and they're very often paired with a robotic arm. The absolute magic here is agility. Because these machines are computer numerically controlled, or CNC, they can be rapidly retooled, modified, and completely regrouped to produce a totally different part within the same family, and they do it with almost zero delay. It's the literal foundation of modern manufacturing agility.
Now, zooming out just a bit, a full flexible manufacturing system isn't just one straight line. Take a look at this schematic layout. You've got multiple machining centers, those are the larger blocks you see, all integrated together. But what really makes this entire system hum is the automated material handling setup. See those little carts? Those are automated guided vehicles, or AGVs. They dynamically move parts and raw materials between the different workstations and inspection areas. They don't have to follow some strict sequential ABC order. They can transport a piece to any machine at literally any time based on exactly what the central computer is dictating at that second. It's like a giant puzzle, forming a dynamic, living system.
And this brilliantly illustrates what that agility looks like in physical reality, a robotic arm operating right smack in the middle of a flexible production line. This isn't science fiction anymore, folks. It is happening right now. These robots handle materials, they load and unload raw workpieces, and they seamlessly transfer parts between those machining centers we just mapped out. It totally eliminates the heavy, hazardous, and super repetitive manual lifting, which means the whole system can run smoothly and, in many cases, completely untended by humans.
So comparing the old inflexible transfer lines directly against modern FMS really shows why this shift is a total game changer. Look at the part variety row here. Traditional lines could only handle a few tiny variations, but in FMS, it can handle virtually an infinite variety. Then look down at lot size. We drop from meeting huge batches of over 100 just to justify the setup time, all the way down to lot sizes of just 1 to 50. And the ultimate result? Inventory levels plummet from high to low. FMS drastically cuts down changeover time, meaning you can produce parts in any order in batches as small as one. That allows factories to respond instantly to fluctuating market demands. No way you could do that in the past. Section 2. Lean and just in time. Because honestly, having all this cool physical machinery is only half the battle. To truly make a smart factory work, you need a profound philosophical shift in how that machinery is actually operated.
This brings us to the absolute bedrock of modern manufacturing philosophy, the stark contrast between a push system and a pull system. In a traditional push system, you're making parts according to a rigid schedule, and you just stockpile them in a massive warehouse, basically crossing your fingers and hoping someone eventually buys them. It wastes space, it wastes capital, and it wastes materials. But modern factories, they operate on a pull system. This means producing parts strictly to order. The downstream customer demand literally pulls the product through the factory floor. You only ever make something when it is actually needed.
And this pull system is the defining characteristic of just-in-time, or JIT, production. Now, this originated with companies like Ford and John Deere, but it was fully implemented on a massive scale by Toyota back in 1953. The ultimate goal of JIT is zero inventory. Really think about what that means.
Supplies arrive exactly in time to be used, parts are made just in time to be assembled, and finished products are completed just in time to be shipped and sold. It is a systematic, relentless war on waste of materials, tied-up capital, and wasted physical space on the factory floor.
Okay, I absolutely love this analogy. It really drives the concept home perfectly. Imagine a lake that is covering a bed of large boulders. The water level represents your inventory. If you have a ton of inventory, so high water, you literally can't see the boulders underneath. Those hidden boulders are your production problems, machine inefficiencies, bad suppliers, quality defects. But when you lower that water level by reducing inventory through just-in-time production, suddenly those boulders are completely exposed. You hit them. And while that sounds bad, it forces the factory to immediately identify and fix the underlying problems, instead of just using a massive buffer of excess inventory as a safety net to hide poor quality.
Now, just-in-time is actually part of a much broader strategy known as lean manufacturing, and there are 5 precise steps to this methodology. First up, identify value, and this is absolutely crucial. It must be defined from the customer's perspective. If an activity doesn't add value for the customer, it's waste. Second, identify value streams. This means mapping out every single action from the initial design all the way to physical production. Third, make it flow by eliminating any idle time between operations. Fourth, establish pull. So like we said, you only build what's explicitly ordered. And fifth, achieve perfection. This relies on constant, continuous improvement, which the Japanese call kaizen. It's an endless systematic loop that builds a hyper-efficient factory over time.
Section 3, the industrial nervous system. We've got our flexible physical machinery, and we've got our lean philosophy. Now we're going to move into the digital layer to see exactly how these physical and philosophical elements are actually wired together across the factory. Now, what's really interesting about this slide is the incredible biological analogy used in modern factory design, holonomic manufacturing. The word holon comes from the Greek word holos, meaning whole, and the suffix on, meaning a part of. Think about the living cells inside your own body. They are self-contained wholes, right? But they're also dependent parts of a much larger system. A holonomic factory is designed the exact same way. You have autonomous, self-reliant manufacturing units, say a CNC milling machine and its human operator, that can handle local contingencies totally on their own. But they also instantly plug and play with other holons dynamically, reconfiguring themselves based on whatever the factory needs to build that specific day.
But to make all these separate holons actually communicate seamlessly, we need an industrial nervous system. Enter the Internet of Things, or IoT. Today, every single machine, sensor, and fixture is connected via standard IP networks. But there's a catch. They all speak totally different digital languages, right? Well, that's where MT Connect comes in. It's an industry-standard protocol that basically acts as a universal translator for all that machine data. It pulls the information in real time and shoots it up to cloud-based storage. Suddenly, without anyone even noticing, you have this massive, big data pool covering every micro-vibration, temperature change, and cycle time across your entire facility. And when you gather all that data together, you can create something truly revolutionary, a digital twin. Now, this isn't just a simple 3D CAD model. No way. It is a complete, living computer representation of a physical part. It contains every single piece of data collected from the exact moment it was manufactured, including metrology results and the exact temperatures applied, all the way through its entire service life. Because the physical sensors are providing data continuously, factories can use these digital twins to accurately predict reliability and order preventative maintenance before a physical breakdown ever even has a chance to happen.
Section 4, the factory brain. We've built the body, and we've installed the nervous system. Now we are ready to explore the highest level of smart factory integration, artificial intelligence. It really brings up a provocative question. Can a factory actually think for itself? We've already seen how a facility collects these massive amounts of data. But let's be clear, data collection isn't intelligence. The future of manufacturing is bridging the gap from a facility that merely records what is happening to one that actively reasons, learns from its environment, and solves highly complex problems dynamically, all without human intervention.
This leap is achieved through some very specific artificial intelligence capabilities. First off, we have expert systems. These act as the cognitive faculties of the factory. They use massive databases of knowledge and inference rules to essentially mimic the decision-making of a human expert. They use a heuristic approach to make incredibly high probability guesses when solving problems. Next is machine vision, the factory's eyes. By combining optical sensors with AI,
computers can inspect parts, identify tiny defects, and physically guide robotic arms in real time. Finally, natural language processing allows human workers to query these massive databases using just simple voice commands, rather than having to type out complex code.
So, the crucial point is how this all comes together. To process all this visual, auditory, and sensory data simultaneously, which we call data fusion, factories are utilizing artificial neural networks. Now, the human brain has roughly 100 billion linked neurons. Machine learning algorithms literally try to mimic this exact biological architecture. Instead of just performing sequential, step-by-step computer tasks, neural networks allow machines to recognize incredibly complex patterns. For example, predicting the exact surface finish of a machined part based purely on subtle acoustic emissions and cutting forces. And the craziest part? They learn and get smarter over time by adjusting the strength of their own internal connections based on past data.
Section 5. The economic reality. Now, all of this sounds absolutely incredible, right? Like some sort of futuristic utopia. But, as any focused learner knows, we have to ground all these futuristic digital concepts in the harsh, practical economic realities of the modern manufacturing business. And the absolute reality is, the cost of achieving this ultimate flexibility is remarkably steep. Setting up a flexible manufacturing system is highly capital-intensive. We're easily talking millions and millions of dollars up front. And it is definitely not an overnight switch either. It generally takes anywhere from 2 to 5 years just to install and debug the entire system before it's actually running smoothly. Furthermore, while you might be completely eliminating direct manual labor on the floor, you're going to require a massive shift in human capital. You now need highly specialized, highly paid programmers, maintenance engineers, and data analysts just to keep the whole system alive.
Because of these enormous costs, smart factories actually have a very specific economic sweet spot. And that spot is typically between 15,000 to 35,000 aggregate parts produced per year. Think about it. If you're producing millions of identical, low-variety parts, an old-school dedicated inflexible transfer line is still going to be way cheaper. On the flip side, if you're only producing, say, 5 highly custom prototypes a year, standard standalone machinery is your best bet. But for medium-volume batch production where part variety and agility are absolutely essential, this 15,000 to 35,000 range is exactly where a flexible smart factory perfectly balances agile flexibility with the economics of scale.
All of this paints a totally fascinating picture of our future. We've seen how holonic machines, digital twins, and neural networks are systematically taking over both the physical and the cognitive tasks of the factory floor. But it leaves us with a truly fascinating, provocative thought to ponder. As digital twins and AI fully take over the factory floor, what exactly will be the future role of human intuition in manufacturing? As machines literally learn to think for themselves, perhaps our human role shifts entirely away from doing the work to orchestrating the creativity of the system itself. It's a profound, evolving partnership, and it's definitely one we are going to be watching very closely. Thanks so much for learning with us today on This Explainer.